All right, so we're going to try to do a quick little overview of probability here to either refresh or to teach you a few key concepts for probability. And so on this first one, we have just the general terms here. I can use relationships among events to find probabilities, and there's a complement, independent events, and mutually exclusive events. So here you have some general information. Mutually exclusive events, no outcome is in both. So when you have two things that are totally separate, you can't have one that's a part of the other. That's mutually exclusive. So if we look at the example at the bottom with the spinner, if A says you're going to spin a number less than 3, and B says you're going to spin a number greater than 5, there's no way that something can be in both of those at the same time. Okay. The second one, independent events. So when you're going to have two different events, and in the example at the bottom of this one, they say you're going to spin a spinner and roll a number cube or a die. When you're doing that, those are two totally different things. So that's independent. So these two things they're kind of different. They relate to, there's still a probability, but different situations. Mutual exclusive here. We have two different situations. The first one says that we have a probability of getting an even number. And the second one says that the probability of getting a 3 or a 5. And so those things are totally different. And then there's one other option, and that's just the 1. So one way to do this problem is the probability of getting the even number. That's 3 numbers in here out of 6 total. And so that's the 3. And then over here, the 3 or the 5, that's 2 numbers. And so you could add those together and get a 6. Now, the complement of that is if you were going to just say, well, it's everything but the 1. So then you could do it's 1 minus 1 out of 6, which gives you 5, 6 also. So two different approaches to the problem. One just is adding up all the possibilities, or the one is like you're excluding the things that are not possibilities. So that would be that one. So let's try a problem. We've got a box that has 100 balls in it, and then 30 of them are purple and 10 of them are orange. And if you select a ball at random, what's the probability of a ball purple or orange? So purple's in the box again, we're 30. This is for A. And then add on 10 were orange, and in the box we're 100. So that's 40 out of 100, or 4/10, or 2/5, or 0.4, or 40%. Now, you could have done that maybe the other way too, because you could have said, well, 1 minus, well, how many of the others are in the box that don't work? And if there's 40 that work, there were 60. So that would have, you could have got the 40 by thinking of it that way with the complement sort of reasoning. B, the ball is not purple and not orange, and not orange. So what's the probability of each of the following? So then it would just still be that it's all of the other colors, which is how many others other than the purple and the orange. If there's 30 purple, 10 orange, there's 60 that it's neither of those two colors. So that would be the 6/10 if you divided both by 10, 3/5. It could be that is 0.6. You could put that as the 60%. And so it could be the complement to the 40%, which would be the 1 minus 40%. Also would give you the 60%. All right, let's move on. So the next one says we have A and B over there, and they're mutually exclusive. See how they don't overlap at all? So that's why they're mutually exclusive. And that if you added A and the probability of A and B both occurring, is what this is saying, that's 0 because they can't both happen. And if you look at the complement, that's everything outside of here. So if we're talking about the complement of A, that would be 1 minus the probability of A. Kind of did that on that last problem. This next example is we can use an area model to show probability. Let's just jump over to the example. It says you have a video game. There's a screen that's 34 by 20. And then inside of here, there's these two circles, each with radius 6. And then the area that overlaps in here is 20. And then that's like some spaceship or whatever. And then there's a black hole, and they're wondering what's the probability that the ship could end up on the black hole. So the area of these two divided by the total area of the region. So if you do the 20 times the 34, 2 times 34 would be 68, add the 0. That's the area of the whole thing. And then these circles, pi r squared is the area of a circle. So if we do pi times 6 squared, that would be one of these circles, but we have 2 of them. So 6 squared is 36 times 2 is 72. So that's 72 pi, but then this part that overlaps, you have to subtract that out. And then that would be the area of the 2 circles divided by the area of the whole thing. And then you could maybe reduce that because see all these even numbers in here, 4 probably divides in everything. But that would be a way of figuring the probability there. You got to take away the overlapping amount. So it's like the area or probability of this one minus that in the shared region there. And that's what you see here for the formula. So the probability of A minus B, but if you add those, then you counted this in here twice because you counted it once for A and once for B. So that's why you have to subtract one of those out. Let's see, independent events. This one's talking about these green and violet marbles. And it says a marble's chosen at random from the jar and replaced, and another marble is chosen at random. But since it's replaced, the probability is independent each time. They aren't going to be affected by the marble. Let's take a look at the next example, and maybe this will bring it out. So you have these 10 cards in a box, 5 red, 5 black, and you're going to select 2 cards. Now you have 2 situations. A up here, a card's chosen and then replaced and then the next card. So when you do that, those are going to be independent because the card is placed back in so that it starts all over again. But when you look at B, a card's chosen and then it's whatever card you choose is kept out. So when you go to B, if you choose the black, the next time you're going to only have 4 blacks in there. So that's going to affect the second time. So B is dependent. Again, you had these 10 cards, 5 black, 5 red, and on the second one, so you're not replacing the card after you pull it out. So if I pull out a black the first time, then the next time there's 1 less black. That's gonna, the second event depends or changes based on what happens the first time. And so then the screen's just kind of, again, explaining the probability independent events. If you're looking for 2 things, so then the probability of the first one, the second one, you're going to end up with the multiplication or product of those 2 because you're going to take the first probability and then multiply it times the probability of the second one. So a 4 on the die, that's only one of the 6 sides. And then a heads, so that's a half. And then the probability of both those things happen is their product. Spin a spinner 2 times, assume the probability of blue is 1/3, and the probability of orange is 2/3. What's the probability of getting the same color both times? So if I do 1/3 blue and the next time 1/3, that would be 1/9 of the time. And then on the orange, I would do 2/3 times 2/3, which would give me 4/9. And so to get the probability of getting the same color both times would end up being 5/9 of the time, because then if 1/9 of the time I get both blue and 4/9 of the time I get both orange. So just getting the same color, doesn't matter whether it's the same blue or same orange, would be the two of them added up. And that's just a summary we started with. The second lesson, conditional probability. Now this is like, how do you calculate a probability? And the biggest thing I want you to get here is kind of the notation. So if you're looking at this notation, what it is what's the probability of you having a sophomore given, or if you know they're in drama. So if you come back up here to this table, we know they're in drama, so we're only looking at this column. And then the probability of a sophomore, so it's 3 out of the total in drama, 17. But it's this notation I want you to really at least have an idea of what that means there when it's written with that line in the middle. What's the probability of getting a sophomore if you're given, or you know that what you have to choose from are just the dramas? So there can be some other ways that they write this or that it follows up, but just that general idea of what that means in that example. Here they're just explaining that again. So the probability of A given B, and the probability of B given A, and the way that they write that with the notation. Okay, so then that's the big thing there. Now this next one, I don't think we're going to go all the way through the permutations, combinations. I'll show you the formulas just so you know they exist. They're on this page here. The permutation in algebra, how it would work in an example. I'll show you when we get to the problems. So this is talking about Manuel, and we wants to advertise these pizzas, and you've got the different sizes, large and mediums. You got the different types of, 2 different types of crusts. So if I just go to large, I still have the 2 crusts. And then after we get that, we still have the 3 different toppings. So if you look at all the way down here, on just the large, we have 6 different possibilities. And then if you go to the mediums and you have to add all those on again, you've got 12. So how do you get the total possibilities? This is called the fundamental counting principle. The 2 sizes, large and medium, times the 2 types of crust, and then times the 3 toppings. And so that would give us a total of 12 different pizza combinations that we could end up with. All right, so let's fundamental counting principle. This is just in general what we were just saying. So if you have M things and then N things and then P things, and you want to know how many different combinations or how many ways you can end up with them, you would multiply those 3 numbers. All right, so Gabriella, 3 songs. And then she has an organized list, like she wants them in a specific order. How many ways could she do that? So sometimes you'll see it over here where they have, if it's in order, you'll see. So sometimes they'll use this chart here. If you haven't used any yet, there's 3 choices. She had 3 songs. She wants them organized. After she puts one of them there, then there's 2 left for here, and there's 1 left for here. So 3 times 2 times 1, that shows the 6 different possibilities here. So you'll see that down here where they do n minus 1, n minus 2. I think that gets a little confusing, and all the way down to get to 1. Or right here is what I was writing. Now the exclamation point means factorial. So if there had been 4 songs, would have been 4 choices, 3 choices, 2 choices, 1, 4 exclamation point. And so if you multiply that out, 12 times 2, that's 24. All right, and then this is just showing if it had been 8. And then if the order doesn't make a difference, then you got to take out all of the duplicates. So each of the songs could have been rearranged in 3 songs in 6 different ways. So if there was 8 songs, that would be 8 factorial, but you got to divide out if, in this case, the order of the songs, because normally you wouldn't necessarily care what order if it's just picking those, let's see, this is 8, 1, 2, 3, 4, 5, choosing 5 songs. So, yeah, so let's move on after that. That's what we just went through. So this permutation is when the order doesn't make a difference. So you have to divide by this that takes the duplicates out, because it doesn't, if the order doesn't make a difference. The combination, like a combination padlock, this is like the wrong thing for that, because on a combination padlock, order makes a difference, but combination really does not make a difference here. So your formula for dividing out the duplicates here. How many ways can a camper choose 5 activities from 10? So choosing activities doesn't say you care about what order they're in. So this would be a combination, because the order doesn't make a difference. How many? You have 10 to choose from, and you're going to choose 5. And you could do this right in like Desmos like that, or you can do the 10 times 9 times 8 times 7 times 6 possibilities. And then the order doesn't make a difference, so you got to divide out the 5 factorial ways of rearranging those. And again, that's this combination formula right here. I don't think you're going to have to do those. I'll kind of just let you know that's there. You can look those formulas up if you ever need them.